Welcome back, students. We're almost there. Nearing the end of the semester. We're going to do the inverse tangent and secant. Let's go back and look at what those look like. They were ugly. Tangent's got that look going on, and secant, I don't have the highlighter on. Tangent's got that look going on, and secant's got that look going on. And we're going to talk about how to recognize, look at what you're looking for. I went and copied these equations down below. I grabbed these and I copied them and put them down in that section down where we're going to use them again. So I put them here. I did not cross those out, but I should. We're going to stick with these. Notice that while this had a minus in it, and that way we were able to use the sine squared minus equals the minus ones. These have a minus in it. This version doesn't. Or when it does have a minus, the minus is the constant is being subtracted. So that's how we're going to distinguish between them. Okay? Where were we? Right here. So having that positive in there is going to lead us to choosing one of these. This setup looks pretty good for it. If I line up tangent squared theta with x squared theta. So that's what I did. So tangent squared theta equals x squared. We take the derivative, or take square root. We get x equals tangent theta. Remember, this is technically absolute value of x. Tangent didn't have that problem here. Just secant theta does to address domain issues. I drew my triangle. I don't think I used the triangle. Derivative of tangent theta is secant squared theta, so dx equals secant squared theta d theta. We're going to replace our x squared with we're going to replace our x squared with tangent squared. Okay? I don't think I need that right there. So we're going to replace it like that. And then we've got 1 plus tangent squared. We're going to use that sub here, right there. That becomes secant squared on bottom. We had a secant squared on top from our dx. Those cancel. We get the integral of d theta, which is theta plus c. So theta equals tangent inverse of x. That's how they came up with that formula up above. So when you see a plus, you're going to want to use the tangent squared one. When you see a minus, it's usually a minus will have a sign. And you'll see when there's an extra variable outside, when we have the secant, we'll look at that in a second. Let's do this one a little bit more difficult, though. That formula they give you with the A and the U is hard to use. Let's just make this look right. What I did, we're dividing. We're taking the 25 plus 4x squared, and we're multiplying by 25 over 25. And when I do that, I put the bottom 25 in. That becomes 1, and I get 25 on bottom times 1 plus 4 over 25x squared. That's what I was doing right there. Okay? So maybe I'll show that. This leads to that, which leads... that's not going to look good on the printing. We'll leave it like that. Make that look more like a 5. And then distribute that in right there. All right. And that leads to that. All right, so I got a 1 over 25 on the outside. I've got 1 plus 4 over 25x squared. We're going to make that look like 1 plus tangent squared, which means this equals that. So we take the square root of both sides, we get 2/5 x equals tangent theta. Take the derivative, we got our differentials. 2/5 dx equals secant squared theta d theta. I only have a dx here, so I just solve for dx. I multiply by 5/2. So we will replace dx with 5/2 secant squared theta. We will replace 4/25 x squared with tangent squared right there. As I've done here, there's my dx. That's my dx. And that's my 2/5 x squared. So this is secant squared theta. So we apply that here. The bottom is secant squared theta. The top is secant squared theta. I multiply 1/25 and 5/2. You get 5/50, which is 1/10. So I got a 1/10 outside. The secant squareds cancel. I just got 1/10 the integral of d theta, which is 1/10 theta plus c. I wrote it like this, but it's really more coming from that. Theta equals tangent inverse of 2x over 5. So we started with this. We ended with this. Does that look easily doable using that formula right there? We had a 1/10, which makes it look like a is the square root of 10, but it's not. The u on the inside only works like it requires a chain rule stuff, and that formula doesn't show the chain rule. So it's a very shitty formula. Don't use the formula. That's our final answer. All right, now let's try one with limits of integration. I hope I don't fuck up the limits here like I did in the last problem. X squared plus 4, I'm going to factor out a 4 so that it looks like the tangent thing. So I'm going to have a 1/4 out front, which I don't know where it went. Did I actually do that? Let's see what I did. 1/4 x squared plus 1 equals tangent squared theta plus 1. We get 1/2 x equals tangent theta after subtracting 1 and taking the square root. So theta is going to equal tangent inverse of x over 2. I did x equals 2 tangent theta. That's what I did. So I went with a form that didn't factor out the 4 till later on. So I plugged in 2 tangent theta. I didn't do the factored form. I just did the 2 tangent theta right there, which gives us a 4 tangent squared theta on bottom plus a 4. We got our derivative dx equals 2 secant squared d theta, 2 secant squared theta d theta. So that goes here. And I redid my limits. When x equals 0, theta equals tangent inverse of 0. When does tangent theta equal 0? It equals 0 when theta equals 0. This is when I plug in 2, I got when does tangent theta equal 1? That happens when theta equals pi over 4. So that allows us to change our limits over here to 0 to pi over 4. So this is what from the dx. I'm going to put the 2 secant squared theta on top. I'm going to factor out a 4. And by factoring out a 4, I've got 2 over 4 out front, which becomes the 1/2. Okay, then I got secant squared theta over tangent squared theta plus 1. Oh shit, I should say pi over 4. Tangent squared theta plus 1 is secant squared theta though, so they cancel. We've got 1/2 from 0 to pi over 4 of theta. Integrate that, that's just 1/2 theta from 0 to pi over 4. I got 1/2 times pi over 4 minus 0 is pi over 8. So that'll be our final answer there. All right, so here we got absolute value of x on bottom with x squared minus 9. So when that, like for the sine ones we did, the sine one would have had like a 9 minus x squared. Here we got an x squared minus 9. So like we can't make sine squared, the sine squared formula does not equal that. We can't force it to equal that. So we got to use the tangent one. Okay? So let's summarize that a little bit right here. If you have like on bottom 1 minus x squared or something like that, something you can make look like that, factoring stuff out, or 1 minus u squared after you factored some shit out. This is where we're going to use sine theta. We're going to go with the sine squared theta version. When we have u squared minus 1, like we did, we had u squared plus 1, like the tangent, or u squared minus 1 with another u out front. These are two different lines here. Let me separate those. If you can make it look something like that, these are both going to lead to using one of the tangent or secant. But they're both from the same equation. You just manipulate it by either adding 1 to get the tangent squared theta plus 1 version. Okay. So we got this. I factor out a 9 so that I have it doing minus 1 because I want it looking like minus 1 because I have a minus 1 here. Now that I got a minus 1 there, you'll notice if I multiply the 9 back in, 9 times 1/9 is 1. 9 times minus 1 is minus 9. I get back to the original. I can now match up secant squared theta with 1/9 x squared. So I'm equating the radicands here. Putting that in for the radical. We get 1/9 x squared equals secant squared theta. 1/3 x equals secant theta. It's really technically absolute value here. Okay. And the derivative of that is going to be 3 secant theta tangent theta d theta. So that's what we're plugging in. A lot of stuff to plug in. Take your time. Dx is 3 secant theta tangent theta d theta. I put it on the top here. We don't always have to put it at the end. If the top is a 1, we can just put it on top. Then secant squared theta minus 1 was 1/9 x squared minus 1. So I replaced that with that. Then I had absolute value of x out there. Absolute value of x was 3 secant theta. Now that I've replaced everything, Secant thetas cancel out. Those 3's cancel out. This is tangent squared, and we take the square root of that. Those cancel. This is going to cancel. We're just left with the d theta on the inside. We still have the 1/3 on the outside, though. So when we integrate this, we get 1/3 theta plus c. Coming from up here, theta equals secant inverse of 1/3 x, or x over 3. So that's what we put in. And it should be absolute value of x. Three is already absolute value. It's already positive, so we don't need to have the absolute value on the 3. And that's our answer. I told you you're not going to like these inverse trig functions. Working with these trig functions suck. But that's the end of this madness right here. All right. 5.7 is done. We got one section left. One section to really bake your noodle. It's got some cool stuff. St. Louis Arch, the Golden Gate Bridge, shit like that's in it. But we'll do that in the next video. Peace. Stay ornery, my students. Stay ornery.